Welcome back, everyone. So this video we're going to be talking about regular expressions and finite state automata. So let's get into it. So there's quite a bit to talk about today, so sorry this is a little bit long. We're going to introduce the concept of finite state machines. We're going to introduce regular expressions. We'll talk about the relationship between the two, and I will also show you how to verify whether something matches a regular expression in Python. And we'll talk about a few different types of finite state automata and also how we can use them. So this is actually a topic that is much bigger than just this course. It doesn't have anything specifically to do with Python programming, although I'll try to show some Python examples. But it does relate a lot to some other courses that you'll take in the future. So first of all, sometimes the phrases finite state automaton, which is the singular, or automata for plural, is often used interchangeably with finite state machine. Personally, I call it a finite state machine, but textbooks tend to refer to them as finite state automata. Automata is just another word for machine, so they're basically the same thing. An FSA is really just a model that describes how we can transition between states. So here's an example down here about a lamp, and you can see that we've got two states. There's an on state and an off state, and then there are transitions shown here as arrows. And if we want to transition from the off state to the on state, we just turn the lamp on. And if we want to go from the on state to the off state, we just turn the lamp off. And if, by the way, you want to create some finite state machine diagrams of your own, this website down here, madebyEvan.com/FSM, is actually a pretty cool editor for these, which I used for all of the diagrams in this lecture. Okay, so one of the characteristics of a finite state machine is that given the input and knowing what state we're currently on, we can then, it's a very simple matter of determining which state we're going to transition to. So really it just kind of boils down to something very similar to an if statement. So here's another really simple finite state machine, almost the same, but this is like a flashlight. Whereas unlike a lamp where we have an on position and an off position, there's just a button that we can just toggle. So in this case, if the flashlight is off, we click the button and the flashlight's now on. And if we click the button again, the flashlight's off again. Almost exactly the same thing. The key here is that the two transitions are labeled the same. It's the same action that we perform in order to turn the flashlight on as that we use to turn off the flashlight. All right, so what we're going to do is we're going to start out with an exercise here. We're going to build our own finite state automata. We'll just build one in this lecture, and then we'll build a few more in the demo part. But this is a simple one. All it's going to do is recognize whether or not a string that we get is a binary number that has an even number of digits. So the number of zeros or ones individually doesn't matter, but the total number of zeros or ones matters. And if that happens to be an even count, then we'll say that finite state machine accepts the string. And if it doesn't have an even number of digits, or it has some characters other than 0 or 1s, then we can say that the finite state machine rejects the string. Okay. So first of all, let's try to think of the states. This is the usual mental process that I go through. If I'm reading through a binary number, I could think of a possible 3 states. Maybe just to keep things simple right now, I'll just come up with 2 states. The first state would be even, and the second state would be odd. So even represents the fact that I've read an even number of binary digits so far, zeros or ones, and odd represents the fact that I've read an odd number of digits so far. So imagine I'm on the even state. So up until now, I've read an even number of zeros or ones. What kind of transition is possible? Well, there's really just one transition possible. I encounter a new binary digit, either a 0 or a 1. And previously had an even number of digits. Now I must have an odd number of digits. That's how those numbers work. So if we get a 0 or 1, then we transition to the odd state. And similarly, if we're on the odd state and we encounter a 0 or 1, then we transition to the even state. So that's pretty easy. And now we can just turn this into a diagram so that it looks like this. There's one new diagrammatic technique here. I'm using a double circle to represent an accept state. because if we end up stopping, as we're reading through the string, we stop on the odd state, then clearly this doesn't match the original condition. We want a binary number that has an even number of digits. So if we end up landing on the state even when we finish reading through the string, then the string matches. So that's called an accept state. So an accept state is typically represented using a double circle, as you can see here. All right, anyway. Now, if I wanted to get a bit more complicated, I could handle the situation if I encounter a digit other than a 0 or 1. And depending on the context, that may make sense. For example, if I'm asking the user to type in a binary number, they could type in something other than zeros or ones, in which case I might want to have a third state, which is the reject state, because if I ever encounter anything other than a 0 or 1, it's not a binary number, and certainly it doesn't match this condition. In this case, I've chosen to go with the simpler one here, but you can probably imagine I can extend this quite easily, create an additional state called reject state, and there are transitions from both odd and even that are triggered whenever I encounter anything other than a 0 or a 1. And there's no transitions out of that reject state, because once I encounter a non-zero or 1, then no amount of zeros or ones is going to recover the fact that it's just not a binary number. All right, so in this example, we're going to simulate parking. So for, let's say, a parking device where you have to insert coins in order to pay for your parking. In this situation, the parking costs $3. Maybe not very realistic from an economy standpoint, but let's say that it costs $3. We're going to create a set of 4 possible states. So the 0 state is the start state. We haven't paid any money, so we've paid a total of $0. So all of these states are just named after how much we've paid so far. And we can transition from the 0 state to the 1 state by paying $1. And we can transition from the 1 state to the 2 state by paying $1. We can transition directly to the 2 state by paying $2, from 2 to 3 for $1, and from 1 to 3 for $2. Okay, so there are the transitions in this case. We're ignoring things like, requesting your money back or whatever, but these are all the possibilities of getting to $3, assuming that we only have $1 and $2 coins. Let's go through a sample scenario. So we start at the 0 state, we haven't paid any money yet, and we put in $1. So that takes us to the 1 state because we've paid a total of $1 so far. Then we put in another $1 coin. That takes us to the 2 state because we've paid a total of $2 at this point, not enough to get us into the parking lot. So we pay one more $1. That brings us to the 3 state. The 3 state is an accept state, so that allows us into the parking. So let's try the very same finite state machine again, but with a different sequence of inputs. The first thing we're going to do this time is we're going to pay $2. So starting at the 0 state, we insert a $2 coin. That brings us directly to the 2 state this time. Then we insert a $1 coin. That brings us to the 3 state, which again is an accept state. So that finishes and accepts us, allows us into the parking lot. And for the sake of completeness, let's do one more example. So starting at the start state as usual, this time we insert a $1, bringing us to the 1 state, because we paid a total of $1. And then we insert a $2 coin, bringing us directly to the 3 state, because we paid a total of $3. And that's an accept state, so we're allowed in to the parking garage. Okay, so with the idea of what a finite state machine is in your mind, let's talk about regular expressions, and then I'll try to bridge these two concepts together. And I don't really know why this is, but people are somewhat fearful of regular expressions. Here's the trick to regular expressions. So this is just a little meme that I found online to kind of indicate what we're talking about. They are kind of confusing. You can see an example of a regular expression here in this 6th panel here. And so it's a big, long regular expression. It's got lots of brackets. And obviously there are multiple parts to the regular expression, but the way to understand this is to simply understand each individual part bit by bit. And then it's far less confusing. So as you start to learn what some of the symbols mean, like backslash, for example, means something special. The curly brackets, plus, and the dollar sign, and so on, they mean something special. Then this is quite understandable. And I actually have seen significantly worse regular expressions than that. So let's put regular languages in the context of other languages. So a regular language is something that we want to pay attention to because it's something that a regular expression can recognize. That's basically the definition of a regular language. And a regular language is something very, very simple. So examples of things that are regular languages include stuff like function names, variable names, math expressions, that sort of thing. Some math expressions are actually context-free languages. So one thing that's really important to know is that not all of these languages are completely disconnected. They're part of a hierarchy, and so you can see I've got a diagram labeled Chomsky's hierarchy, and this is talking about the relationship between different types of languages. So at the center we have a regular language, which is very simple. So an example of a regular language would be what constitutes a variable in Python. And then outside of that, we have a context-free language, which could include things like XML or HTML. And then beyond that, we have context-sensitive languages, which includes things like Python and to some degree English. There's some things in English that make it not quite context-sensitive, but for the most part, you could take a subset of a very understandable and useful subset of English that was context-sensitive. And then all the other languages beyond that are a little bit more complicated and not something that we regularly encounter. So shown here is the recursively enumerable ones. You can see that regular languages are a subset of context-free languages. So regular expressions, they're actually two different major types of syntax that are used for regular expressions. They're just a notation that's used to describe some rules that we can use to recognize a regular language. And there really are just four main symbols in regular expressions, but we also have some additional extension symbols that we are going to use in order to make our regular expressions a little easier to understand, because these can get quite long if we only use these four symbols. Well, let's go through the basic symbols first of all and see what this is all about. So if we just see a dot or a period or a full stop, that means match one single character, and it doesn't matter what character it is. It could be something that's printable, something that's not printable, it could be a space, it could be an A, it could be anything. And then we have the vertical pipe or the OR symbol, commonly used as the OR symbol in many programming languages. This is called the union, but for me it makes more sense to use the word OR because it really means OR. So for example, if I have A bar B, that means either an A or a B, okay, whereas the dot means literally any character, A or B, or lots of other things. With the bar, you can reduce the set to just a limited set that you're willing to accept. So in our case, for the binary number, I could do something like 0 bar 1 to represent either a 0 or a 1. And then we have our first of the many closures that are available in regular expression, which is the asterisk symbol here, or the star symbol, is used to represent a closure. And what that means is the thing that precedes this symbol is going to be repeated either 0 times, in other words, it's not going to exist at all, or more times. So it could exist 0 times, 1 time, 18 times, 1,000 times. So these can be used together. So for example, if I want to represent 0 or more binary digits, I could say 0 bar 1 and then asterisk. The asterisk would mean I want 0 or more of those. The problem is the star works on only the very immediate thing that precedes it. And so in that case, if I literally just wrote 0 bar 1 star, then the star would operate only on the 1, not 0 or 1. So if I do want it to represent, I do want it to affect the 0 or 1, I have to use brackets. So that's why we also have brackets as our fourth notation. So for example, if I wanted to represent 0 or more binary digits, I would do brackets, 0 or 1 and bracket, star. And that would mean 0 or more zeros or ones. Here's another example. So you can see we've got A star, bar, dot, B star. So it's got most of the symbols. It's got 3 out of 4 of the symbols. And what this means is a sequence of 1 or more A's or a single character followed by 0 or more B's. So let's go through that piece by piece, because as I said, if you look at it in small bits, it's understandable, but looking at a full regular expression can sometimes be a little bit overwhelming. So let's look at the part before the bar. Remember that the bar means or. So we have an A followed by A star. So A star by itself means 0 or more A's. And then since I've got an extra A in front, this means 1 or more A's. So I don't want to have 0 A's. It's only possible for there to be 1 or more A's. So I put in an actual A. I've literally just hard-coded an A here to say there has to be an A if this part of the expression is to match. Remember that the dot represents any character, so this would represent a 0 or an underscore or an enter. And then we have B star. Again, B star means 0 or more B's. So that's why this is any character at all, including a B, followed by 0 or more B's. Okay, and this is a regular language, and this regular expression can be used to recognize it. So we have some extension symbols that actually make this a lot easier to do so that they don't end up being really, really, really long. Longer regular expressions are probably going to be more intimidating. So one thing that we can have is another closure, the plus operator, and the plus operator means 1 or more. So just like we used with the A, we had A star. Instead of doing that, if we use the regular expression extensions, we can just use A plus. A plus means 1 or more A's. All right, and question mark means literally either 0 or 1. So we can't have more than 1. We can only have 0 or 1 of them. So the question mark actually kind of makes sense that they use the question mark symbol. It means that there's an optional component. So this could be used, for example, for a phone number where you don't want to recognize area codes in some cases, and you do want to recognize area codes in another circumstance. There's also the curly bracket notation, where we can actually specify in the curly brackets, we can put just a single number. That'll mean I want to recognize the same thing repeating exactly 5 times. So for example, if I say A, curly bracket 5, close curly bracket, that means I want 5 A's. That's just a short form for saying A, but it's possible. And of course, you could put a bigger number in that curly bracket, saving you a lot of typing. If you have 2 numbers in there with a comma in between them, then that gives you a range. So in this case, if I were to say something like B, curly bracket, 2 comma 5, close curly bracket, that means either 2 B's or 3 B's or 4 B's or 5 B's, any of those possibilities. And if we leave one of these numbers out, but we keep the comma there, then it means, so for example, if we just have curly bracket comma 5, that means up to 5, so between 0 and 5 occurrences. And if we were to say 2 comma curly bracket, then that would mean at least 2. So this gives us a lot of flexibility in how many of a particular repetition we want to see. Then there's the square brackets. The square brackets allow us to choose in a much simpler way than using the pipe, using the vertical bar. So in this case, the square brackets allows you to specify any number of characters inside the square brackets, and it'll match any one of them. So it's basically the same. What we have here is just a short way of representing the exact same thing if I were to say A bar, B bar, C bar, D, all the way to Z. Okay, so in that case, that's a really long expression, and this just allows you to shorten it. And you can also use the characters without the dash in between them. So for example, you could literally type in A, B, C, D, E inside the square bracket, and it will allow you to choose any one of those A, B, C, D, E. You don't need commas or anything like that between them, just individual characters. If you put the caret symbol, or this little triangle shape at the beginning, what this means is any character except for the ones in these ranges. So all the other characters, this has to be the first symbol in the square bracket, but all the rest of the characters are characters that we will reject. We don't accept any of these characters, but we accept all other characters. And since there are some common ranges that we're going to use on a regular basis, there are some built-in, they're called character classes. And I'll mention 3 of them here. \s simply means any kind of space character, so that includes spaces, tabs, new lines. Then there's word characters, \w, that matches any word character. So that includes lowercase, uppercase, digits, and underscore. And then \d, it matches any digit character. So that matches any digit character from 0 to 9. So these can make it a little bit easier. I guess the digit one only saves you a couple of characters. But the fact that it has a D in it, it kind of reads more like a digit as opposed to some square bracket expression. So it can add to the readability of your regular expression, which I think is a good thing, because if you go back and realize there's a mistake, it can help you to repair that mistake. All right, so here's an example. We've got some square brackets, and inside here we've just got a bunch of characters, including some ranges. So we've got from A to Z lowercase and from A to Z uppercase, and also just an underscore tucked in. So that means it's literally going to recognize a single letter, uppercase or lowercase, or an underscore. And then after that, a word character, which if you remember, a word character includes these same characters over here, except it also includes digits. So this is going to be every letter or underscore character followed by every letter or underscore or digit character. Okay, and this is 0 or more of those word characters. So this could be used, for example, for a simple recognizer for a variable. So these two variables here, mark sum1 and class underscore average, they would both match this regular expression here. Okay, here's another example. So you can see we've got 1 dash, that's in brackets with a question mark. So that means either this 1 dash is included, it will match, but if it's not included, it will also match. So this is optional, remember 0 or 1 occurrences. And then we've got the digits 0 through 9 repeated 3 times. That's what the curly bracket 3 means, exactly 3 times here. And then a dash, and then 0 through 9 repeated 3 times. This again could be \d, curly bracket 3. That would work fine too. Or \d, \d if you wanted to. There's a lot of different ways that we could represent the same expression. And then, so anyway, this is saying we have 3-digit characters followed by a dash, followed by 3-digit characters, followed by a dash, followed by 4-digit characters. So this will recognize a phone number like this. It'll also recognize a phone number that maybe just 905-721-8668 without the 1 dash in the front. Okay. So for our first example of a regular expression being processed using a finite state machine, we're going to consider the regular expression A plus, B, C star. So this regular expression means we have to have at least 2 A's, a B, and 0 or more C's. So we're going to have 4 states: the start state, the A's state, a reject state, and an accept state. So let's go through one at a time and consider the transitions. From the start state, if we encounter an A, which is really the only acceptable thing, then we go to the A state. Anything other than an A takes us to the reject state. Then from the A state, we can encounter more A's, and we stay at the A state if that's the case. If we encounter a B, then we move on to the accept state, and anything other than an A or a B moves us on to the reject state. Now from the accept state, we can encounter C's. Any number of C's, including 0. If we encounter a non-C, then that takes us to the reject state, and then from the reject state, there is no way out. So anything that we encounter, star remember means any character, then we stay in the reject state. So let's trace an actual sample string here. So we encounter an A, that takes us to the A's state. We encounter another A, that keeps us in the A state. We encounter a B, and the B takes us over to the accept state. We're good so far. We encounter a C, which is also good. That keeps us at the accept state. Then we encounter another C, again, same thing. Keeps us at the accept state. And finally, one more C. The final string is A, B, C, C, C. We end at the accept state, therefore, this is an accepted string. So for the second example, we're going to use the exact same finite state machine for the same regular expression, but we're going to try it with a different string. Okay, so remember that the regular expression requires that there are 2 or more A's. So it's an A followed by 1 or more A's, followed by exactly 1 B, followed by 0 or more C's. Okay, the string that we're going to input is close, but not exactly a match for this regular expression. So we're going to start at the start state, and we're going to encounter an A. So far, so good. It's going to bring us to the A's state. Then we're going to encounter a B, which is also good. That takes us to the accept state. So far, so good. But then we read a second B. That's actually not allowed. So that transition brings us to the reject state because we're expected to only have exactly one B. So now that we're in the reject state, there's no way out of the reject state. So no matter what happens from here on out, we're always going to end up in the reject state and the string is going to be rejected. So we are going to encounter a string character, but which normally would be correct if it weren't for the second B. So that keeps us in the reject state, and that ends at the reject state. All right, so one more example for regular expressions in finite state machines. You can see that here that we have a regular expression, which looks somewhat complicated, but in reality is quite simple. It just has two parts to it. First, we need to have either a lowercase letter, A through Z, or an uppercase letter, A through Z, or an underscore. You can see those are all in the square brackets, which means that or. Any one of those characters would match just one time. And then we have A through Z lowercase, A through Z uppercase, 0 through 9, and underscore star. So because of that closure, this means 0 or more of those characters. So this will match variables like just X by itself, variables that have underscores at the beginning, underscores in the middle, underscores at the end. Like even underscore would be a valid variable according to this regular expression. In fact, a lot of programming languages, that's actually perfectly valid. So in order to create this finite state machine, we're first going to need to create a start state, of course. The start state always is necessary in every finite state machine. In this case, we're just going to really need two more states. One for we have a valid variable, and one for we don't. And if we encounter any character that's not permitted, we'll immediately go to the reject state. And as long as, so far, all of the characters match our criteria, then we'll go to the accept state directly. And the reason why this is so simple is because the regular expression literally only calls for a single character at a minimum. All the other characters, the second part of this regular expression, is all optional because it's a zero closure, and the star allows you to have 0 of those characters. So we can go immediately from the start state to the accept state with just a letter or an underscore, uppercase or lowercase letter. So if we encounter anything other than an uppercase or lowercase letter or an underscore, we go to the reject state. If we encounter an uppercase or lowercase letter or an underscore, then we go to the accept state. That's every condition from there. From the accept state, if we encounter a letter, uppercase or lowercase, or a digit or an underscore, we stay at the accept state, and anything else sends us to the reject state. So that's a relatively simple finite state machine for this regular expression. One more thing I forgot to add is the reject state, any other character after going to the reject state stays in the reject state. So in this case, our variable has an M. M by itself is a valid variable, so that sends us to the accept state. Then we encounter an I, which keeps us on the accept state because that's a letter or a digit or an underscore. Then an N keeps us at the accept state. Again, it's a letter. Then we encounter an underscore, which is also acceptable. And it's kind of boring from here on out because it's pretty simple. And then we have a V, keeps us at the accept state because, again, it's a letter. And then an A, again, keeps us at the accept state. And then finally an L, which is a letter, so it keeps us at the accept state. And finally, because that's the end of the string, we know that this is a valid variable. So for this next example, we're going to start with the very same regular expression for variables, but this time the sequence of inputs is not going to match. So again, we need to have a letter or an underscore followed by a letter, underscore, or digit. We've got the very same states. Start state, we need to have an uppercase or lowercase letter or an underscore. Anything else is rejected. So letter or underscore takes us to the accept state. Anything else takes us to the reject state. A letter, digit, or underscore keeps us at the accept state, and anything else sends us to the reject state. And from the reject state, no character will redeem the string, so we stay in the reject state. So again, the asterisk here indicates any character. So let's trace. So first we want to have a variable. The first character we read in that variable is an m. That takes us to the accept state because m by itself is a valid variable. Then we have an a character, which keeps us at the accept state. And then we encounter an x character that also keeps us at the accept state. But then we put in a percent character, which is not permitted in a variable, so that takes us to the reject state. And then we have I. Even though I is valid, the percent wasn't, so we're stuck in the reject state. And then we have n. Again, n keeps us in the reject state. And finally, we have c. C keeps us in the reject state. So in this case, one invalid character is detected in the middle of the string, but that sends us to the reject state and correctly recognizes this as a non-variable. So let's talk about how to do it in Python. And obviously in the demo, we're going to do some examples of this. But for now, I'll just show you the syntax. So there are a couple different functions, and there's a package called the RE, which is short for regular expressions. That package is available in Python, and it allows you to do a bunch of regular expression matching, and you can use it in kind of different ways. So for example, if you use this function called match on a regular expression, and then you pass it a string, it's going to look through this string and see if it finds a match to that regular expression at the beginning of the string. So there can't be any excess characters at the beginning that don't match the regular expression, or this will not find a match. But however, if you just want to find within a string, you want to find out if there are any matches, even if there's some extraneous characters at the beginning or the end, then you probably want to use this search function. The search function will find one occurrence of a match within the string. If you potentially might find there to be multiple matches within a string, so for example, let's say you're looking for a dollar amount, and you want to substitute that dollar amount in, like, you're running a store site and you don't want people to post their prices because maybe the product was on sale then and it's not on sale now, and it might discourage you from buying at a higher price. So what you could do is you could use something like find all. So the find all will actually give you a list of all of the matches that it found within the string. The assumption is that you might find multiple matches. Because Python works really well with iterators, you can also use the find iter function, which does the same thing as find all, but instead of returning a list of the matches, it returns an iterator that you can use to loop over the matches. That could be helpful. You can also use a regular expression to substitute characters. So say, for example, you're looking at some forum posts and you want to look for words that are banned on your forum, and so you use the regular expression to look for certain words, and then you have the subs string here is going to be what you want to put in its place, so maybe ... or something like that, so that you just know that it was censored, and then the string is the actual post before you post it that potentially could contain some of these forbidden words. So the sub function could be useful for that. This is used in a little bit of a different way, which I think is a little bit strange. Instead of on the regular expression calling dot and then the function, you actually just call re dot, which is the name of the module, and then you pass the regular expression as the first argument. But anyway, it works in a little bit of a different way. You just have to remember that. Another thing you might want to do is, we've seen the split function before. The split function allows us to take a string and divide it up into a list of strings based on some kind of divider that we find. If the divider is just a character, then that's easy to do. We don't need to have regular expressions. But what if we want to have a regular expression that could describe what the conditions are for splitting up the string? In this case, we could use a regular expression to match the part of the string that's going to be used to divide up the string. So it could be the case that this is split up with several different kinds of dividing points. They're very different in nature, but the regular expression matches them all. All right, so here's an example of a program. So we first import the regular expression library. We use that to create a regular expression. I'm just using re.compile here, and I pass it the regular expression strings like we've been talking about. So this one here looks for an uppercase letter, followed by 0 or more lowercase letters. And then what we do is we use the match function on the name re, which is the name regular expression that we just compiled, and we give it a string to see if it matches. And so in this particular case, this will actually match Benjamin, because Benjamin is a capital B followed by some lowercase letters. Okay. And match, if you recall, it searches from the beginning of the string. So it's going to find Benjamin, because Benjamin starts right at the beginning of the string. Okay? And match will just be none if we didn't find a match. So you can use a construct like if match to check to see if it matches. And if it does, then match is actually a regular expression result object, which you can use then to get the information about the match. So you can find out where did it begin and end in the string. That's what the start and end functions are here. And then .group will actually give you the text that match that particular regular expression. Okay, and then down below we're using the findAll function, and this one will actually use the same regular expression, name RE, but it'll find all three names in the string because they all kind of match the rule. All right, here's another example. So here we're using the regular expression for the phone numbers. We've got a few new things in here that I just want to explain, but you can see this is the exact same regular expression that we saw in the previous slide. The only thing that's different is at the beginning we've got this caret symbol, and at the end we've got this $sign symbol. Well, in regular expressions, the caret symbol means starting from the beginning of the string, and the $sign means at the end of the string. And since this one dash, or if the one dash is optional, then the first digit of the phone number is immediately after this caret symbol, that means that you can't have any other characters before the phone number starts. The phone number has to start right at the beginning of the string. And then at the very end, you can see the $sign is right where the last of the 4 digits of the phone number are. And so that means that they have to be right at the end of the string. So what we're doing here is, instead of looking for a phone number within a string, we're looking to see if the complete string is a phone number on its own. And this could be used for things like, validating a form. If somebody's typing in their phone number, their email address into a form, I want to make sure that everything that they've typed is a phone number, not a phone number with some other stuff. Okay, so you can see down at the bottom, we've got the reference to the docs page for this. All right, this is another one. Again, in the previous one, we just used the match function. And the match function, if you remember, it searches from the beginning of the string anyway. So using this caret symbol here is a little bit redundant and unnecessary here, because match does that automatically. It doesn't search to the end of the string. So the $sign actually does change how this works. Whereas match by itself without the $sign will search for a string that begins with a phone number but has some additional text after. This one specifically will look for these 4 digits, and then it'll look for the end of the string. So in this case, you'll see we've got the 4 digits and then the end of the string. So it actually matches. All right, here's another one where we're using the search function instead. The regular expression is exactly the same, but now you can see that we've got some text before the phone number and we've got some text after, although just a dot admittedly. It'll still find this phone number within the string here. Okay, and the group output that you can see there, that will just be the phone number and none of that extra text before or after. So why am I even talking about finite state machines and regular expressions together? Well, it has to do with Kleen's theorem. So Kleen's theorem talks about how if you have a finite state machine like the ones we've been talking about, these are called deterministic finite state machines, they express the exact same set of languages as a regular expression does, whether we use the extensions or not. The extensions don't actually make regular expressions any more expressive. But anyway, so maybe in more mathematical languages, we could say a language L is called regular if and only if it can be recognized by a deterministic finite state automaton. So that would be a pretty important result, because we often use regular expressions to recognize patterns. So for example, we might use a regular expression to recognize patterns. Let's say we're writing our own compiler, and I just want to look to see if this function name is a valid function name that the programmer tried to use. I would try to use regular expressions in order to do that. So this result is saying that, yeah, anything that we can do with a regular expression, we can do with a finite state machine, and anything that we can do with this specific type of finite state machine, a deterministic one, we can use a regular expression to recognize as well. So this can be pretty helpful, because very often we'll find ourselves creating a finite state machine to represent the behavior of a certain device or a certain object. So for example, a character in a video game, their actions might be dictated by a finite state machine. And that allows us to write a finite state machine for it. And now we can know anyway that we can determine whether a sequence of characters or a sequence of actions actually follows the regular language, which of course is recognized by a regular expression. All right, so here is an example of a regular expression matching finite state machine. And this one matches the regular expression that you can see here, A followed by BA star followed by B. So this is an A, followed by 0 or more sequences of B's and then A's, 1B, 1A, and then a B. So there has to be an A at the beginning, there has to be a B at the end, and the middle consists entirely of BAs. Okay. So in this case, we've got our start state down here, and I'm trying to use regular expression notation in the actual diagram here. If we get anything other than an A, then we reject it because it has to be an A at the beginning, right? So you can see from the start state here, we've only got not A's and A's. This is kind of like the fancy way of saying not A. Rather than list all the possible other characters other than A, I just say square bracket caret A, which means every character except for A. So if there's anything other than A, we go to the reject state. There's no way out of the reject state, so we reject the string completely. It doesn't match our regular expression at all. But if we encounter an A, then we go to a state which I've just not very cleverly called A. All right, then we have a possibility of a bunch of BAs, which we don't need to have. Okay, but if we do have a B, then we go to the B state, and then we get an A, which takes us back to the A state. So we can do another BA after that, or we could just finish. So at the very end of the regular expression, we have a B, and if we get an A followed by a B, then we go to the accept state. ACC is the accept state here. And that just says, well, an A and then a B is actually acceptable. And then an A followed by BA followed by B is also acceptable. And then an A followed by BA, BA, B, that's also acceptable. So we can go around this loop here as many times as we want. But while we're on A, if we get anything other than a B, because I either have a BA or just a B coming next, the next character therefore has to be a B. So if I get anything other than a B, I go to the reject state. And similarly, if I have a B, the next character needs to be an A because these need to be B followed by A, right? That's what this is. So a B and then an A. So if I get anything other than an A after the B, then I go to the reject state as well. Anyway, so there we go. Another way, by the way, to represent a finite state machine, doesn't look as cool, is in a table where you can show the current state, the new state, and the transition. So in this case, I've written it kind of in English, and then also in the monospace font here is showing what I have in the diagram. So anything but A from the start takes us to the reject state, and A from the start state takes us to the state called A. Maybe I should have given these better names, maybe a capital A or something like that. And a B from the A state was allowed. That takes us to the B state. Just going back to here. A B, when we're in the A state, takes us to the B state. That's this one right here. If I have anything but a B in that situation, however, it takes us to the reject state, and that makes sense. That's, whoops, wrong way. That's this one right here. And if I get an A from the B state, it takes us back to the A state. It's kind of similar to the beginning. So that's just, if I'm in the B state, the A takes me back to the A state. And also from the A state, I can go to, also from the B state, rather, if I don't get an A, then that's not allowed. The only thing that's allowed right after a B is an A, so that takes me to a reject state. So this is possible, and it contains similar information, but it isn't quite as easy to read. With the diagram, I find it easier because you just basically remember, what state am I currently in? So you start on the start state, and then you start looking at the string. And if in this case, let's say, for example, the string is A, B, A, B, A, B, then I say, okay, well, the first character is an A, so that takes me to here. And then B, A, B, A, B takes me to this state, and that's an accept state. So this string must match this regular expression. And also, it matches this finite state machine. Anyway, Now, you may have noticed if you have a keen eye that this finite state machine is not the same as the ones that we've seen before, because this one has a unique feature that none of the other finite state machines had. From the state A, you can actually see that there are two paths, two transitions that are labeled B. So if I get a B, which way am I supposed to go? Am I supposed to go this way, or am I supposed to go this way? So this is actually called a non-deterministic finite state machine. The ones that we've seen up until this point are called deterministic finite state machines. And of course, finite state just means it has a finite number of states, which you can see here. We have 5 states. A non-deterministic one is used because there's no rule that says I specifically have to choose to take this transition instead of this transition, or vice versa. Okay, and so non-deterministic finite state machines are a lot more difficult to implement, but they actually can be used to represent more complicated languages. This one in particular, we don't need a non-deterministic finite state machine to recognize, because I could convert this to a deterministic finite state machine. It would still recognize the exact same language, but there are some languages that can't be recognized using deterministic finite state machines, and those are non-regular languages. Okay, anyway, so let's look at one more example. Here's another regular expression. You can see this regular expression was the one that recognized a variable, and we're going to do this in the demo. I'm going to write some code to do this in Python in the demo, but this is a really simple one, which just says I want to recognize a letter or an underscore followed by a 0 or more word characters. So this is what the regular expression translates to in terms of a finite state machine. We have a start state. From that start state, we can get a lowercase or an uppercase letter or an underscore, and that takes us to the accept state, because we don't actually have to have a second character. We can have literally one character in our variable name. That's allowed. And in many programming languages, even just an underscore by itself is a valid variable name. That's true in Python, for example. But if I get anything else, that's what this is. This is not a lowercase letter or an uppercase letter or an underscore. So everything else, including a digit, for example, sends us to the reject state, because there's literally nothing else that we can start a variable with. It has to be a letter or an underscore. Once we're in the accept state, notice that we don't just automatically stay there. If we ever encounter an invalid character, then we still go to the reject state, even though we were in the accept state. If we encounter something other than a letter or a digit or an underscore, then we go to the reject state. So for example, if I type in x ampersand, the x is correct. In fact, by itself, x is a perfectly valid variable name. But then the ampersand is not a valid variable character, so that sends us to the reject state. And anything, once we're in the reject state, keeps us in the reject state. But notice that if we go to the accept state with the x, for instance, and then I encounter another letter or another digit or another underscore, that's actually allowed, and we stay in the accept state. So these two are equivalent. I don't demand of you that you understand how to take a regular expression and turn it into a finite state machine, or vice versa, but I think it is a good idea as an exercise to get some practice with figuring out how we recognize a regular language using a finite state machine. So for example, if I give you a variable name such as min, you should be able to follow through this finite state machine here and to see why min is an acceptable variable according to this regular expression. Now, regular expression, you can understand the context of how it works, but it's not as easy to trace how the regular expression matches a particular string or doesn't match. But it is much easier to understand how the finite state machine does that. Okay, so let's talk about a few of the other types. We mentioned about deterministic finite state automata, and those are the ones that we've mostly been dealing with in this class. There's also a push-down automata, which is push-down. It's a deterministic finite state machine that has a stack as well. So we have a stack to keep track of previous states, and this allows us to recognize a subset of context-free languages called deterministic context-free languages. These are a little bit more complicated and kind of outside the scope of this class. And then we also have non-deterministic finite state automata, which I just showed you an example of. And these allow us to recognize any context-free languages. And if you remember back to when we were talking about Chomsky's hierarchy, I talked about how context-free languages include things like HTML and XML. And so you could use a non-deterministic finite state automaton to recognize HTML if you wanted to write a parser for it. Okay, so this is the exact same finite state machine that we had before. So this is a non-deterministic finite state machine. And if you remember, the thing that made it a non-deterministic finite state machine was because from this A state here, if I encountered an input B, then it would either send us to the B state or it would send us to the accept state. And given the nature of this, it's not necessarily known what would happen. So what often happens in this situation, if you're simulating this, is you might try to go to one state first, see if that matches. If it doesn't, then you might need to backtrack and then try the other option. And that's why implementing non-deterministic finite state automata is actually more complicated. We're not actually having to implement them ourselves in this class, but just understand that there is an implementation challenge for these that you'll obviously deal with a little bit later when you do compilers. So what do we use finite state machines for? We already talked about regular expressions, but it does actually quite a bit more than that. So we can use this represent machine logic. We'll do a couple of examples like this in the demo. But obviously, if you're implementing a machine, one of the things you might do for really simple machines is you might first create a finite state automaton for it, and then you can then figure out where to go from there. You can write the code for it, for instance, or you can create a circuit in order to implement it. You can also use finite state machines to recognize patterns and genes. You can use it for AI in games. I've got a link here that I invite you to check out in your own time if you want to. It talks about how finite state machines are used in some common video games. Finite state machines are used for circuits that have memory. We're going to deal with that next semester in the computer architecture class. They're also used in compilers and parsing, in particular in the parsing phase. We'll use it for analyzing the individual components of the language. Today we've talked about variable names and function names and things like that as just examples of that. You can also use them in natural language processing, although natural languages are very complex beasts with lots of ambiguity. They tend not to be regular languages, and they tend not to be context-free languages, so they're a bit more complicated to process than computer programming languages. Okay, so let's talk a little bit about the applications of finite state machines. So parsing, for example, here's some HTML. You may have never encountered HTML before, but this is a line of HTML code, and it's called a div tag or a division, and basically it's a section of your page. And it's got a couple of attributes. It's got an attribute called class and an attribute called ID, and class is set to the value title, and ID is set to the value details. And then in between this angle bracket here and this angle bracket here, that's called the opening tag. And then at the end, we also have this slash div, which represents the closing tag. So the opening tag says, well, here's the beginning of the tag, and the closing tag is the end of the tag. And in between the opening and closing tag, we can also have the content of the tag. So there's attributes. The attributes can have values. We've got the opening and closing tag, and we also have the content of the tag. So there's a lot of different parts to this. It's pretty complicated. But nevertheless, unlike a regular language, this is a context-free language. But what I'm going to do is I'm going to use just this little snippet right here. We're going to create a finite state machine to recognize something like this. Okay, so let's actually figure this out. All right, so here we go. This is what I've come up with, and it doesn't have a really great, naming system because the tool that I'm using, it's really great. Doesn't let you put very long names in there. So I'll try to explain what all of these things do. So we've got to start, obviously. And the first transition out of start is if we encounter a less than symbol. I'm leaving out all the reject states here. There's tons of reject transitions that I would need in order to show that. And I think that just adds to the complexity. So maybe just to keep things simple, I just have the transition. The only valid transition into a tag is to encounter the less than symbol. And that makes sense. It's the very first thing that we see here. All of the tags begin with the less than symbol. So now we're in the opening tag when we're doing that. Okay, and we stay inside the opening tag if we encounter a lowercase character or an underscore or a dash. There might be some other characters that are allowed. I'm not 100% sure on that. And then if we encounter a greater than symbol, then we're done. We're actually outside of the opening tag, and we're inside the content of the tag. So at this point in time, this is in between the opening and closing. That's this little bit right here. All of this text in here is allowed. The only thing that we're not allowed to have is a greater than symbol, less than symbol, that kind of thing. Okay, so as long as we're in there, so we just can't have a greater than or a less than symbol. So the less than symbol is the one that I've got here because, look here, it's the ending of the content is when I encounter this less than symbol. And anything else, any other kind of character, we just recognize that as part of the content of the tag. And then I'll encounter the closing tag, which is also marked by that less than symbol. So we've got the less than symbol. We've got a bunch of other characters like dashes and underscores and lowercase letters. You can, by the way, have uppercase letters in HTML, but I'm just, for simplicity, using lowercase letters. And then when we encounter the greater than symbol, the closing tag is also finished. So we enter the except state. We've basically recognized an opening tag and a closing tag. And the thing that I've skipped over are the attributes. So if I just had less than div greater than picnic event details and then this closing tag, that would match that already based on what we've talked about. But we have to match these attributes here. So the attributes are basically name equals and then a value in quotes. So let's look at that. So if I encounter a space somewhere in the opening tag, then I can assume that the thing that's immediately following that space is an attribute name. So I'm going to say go transition to the attribute name state. And if you encounter any of these things, these are perfectly valid characters in an attribute name, just like they are perfectly valid characters in a tag name. So a lowercase letter, a dash, or an underscore, those are all fine. But when you encounter an equal sign and a quote, just like we have right here, equal sign and quote, now I'm no longer defining the name of the attribute, but the value of the attribute. So now I'm in the attribute value. And then when I encounter another quote, that's the end of the attribute value, and I go back to here. And I can have multiple attributes just by going around this cycle multiple times. Okay, so this is obviously not a complete introduction to parsing. It's meant to give you a basic idea of how you might use a finite state machine in order to recognize something relatively simple. Okay. So there's one more cool thing that we can use finite state machines for. This is actually a different kind of finite state machine that we didn't see. This is called a cellular automata. But I'll kind of show you a deterministic finite state machine inspired representation of this. But what this is really neat for is because it allows you to do something really, really simple. And then the result is something that has a lot of complexity to it, which I think is really neat. So we're basically defining something that has a really, really simple set of rules, but at the same time, there's so much possible within this. Like, I don't know if I'd call it a game. It's called the Game of Life anyway, introduced by John Conway. And so it's a pretty cool concept, and a lot of people are continuing to work on investigate this game of life. And basically, it's an idea that instead of just having states, what we're going to do is we're going to have a grid of states. And each one of these grid positions, these cells in the grid, which is why it's called cellular automata, is going to have a state of their own. And the states of the neighbor cells to those states is going to influence the next state. So if, for example, I'm currently examining one of the cells in this grid, I'm going to look at the state of the other cells around the edge. There's going to be 8 cells around the edge, and I'm just going to determine what's the status of those cells. And so there's a lot of different possible uses for cellular automata, but this is like one of the simplest ones, and it already comes up with some pretty cool behavior as a result. So let's talk about what the rules are for Conway's Game of Life. So the rules are literally these 4 rules, so it doesn't get any simpler than that. It's called the Game of Life because it's sort of, in a really, really basic way, it mimics how things behave in the real world and living creatures. And so if we're in this case, we're just going to consider each cell in the cellular automata to be either dead or alive. So it's simply a binary state. You can imagine how you could have states that are much more complicated. This one just literally has just a binary state, two states, alive and dead. And here are the rules. Any live cell that has less than 2 alive neighbors dies. And so we can call this rule the underpopulation rule, perhaps because they're just too isolated and they're vulnerable to the elements, they're vulnerable to predators and stuff. So if you have fewer than 2 alive neighbors, say for example it's just 2 cells by themselves, then they die, because each one of them only has 1 alive neighbor. If you have 2 or 3 alive neighbors, then it's fine. You just survive to the next stage, to the next time step. But if you have greater than 3 alive neighbors, then you die. This is called the overpopulation. It's just too crowded that maybe there's not enough food to go around or whatever. I'm trying to justify these by rules that don't necessarily need justification. But if you have greater than 3 alive neighbors, then the overpopulation rule kicks in and the current cell dies. Okay? And then finally, if there's a dead cell that has 3 alive neighbors, it becomes alive. So we can call this reproduction. So there's no living cell right there, and then the 3 alive neighbors make that cell alive, so they reproduce. 3 alive neighbors, obviously not how things work in most of the animal kingdom, but anyway, it's called the reproductive step. And what's really quite cool about this is, even though these rules are so simple, like it's literally just a statement where you're going to say, we'll count the number of neighbors that are alive. If it's less than 2, then we're not alive. If it's equal to 2 or equal to 3, then we are alive. And if it's greater than 3, then we are not alive. And also, if the cell is dead, and if the number of alive neighbors is exactly 3, then we are alive. So like the rules are so very simple. It just takes a few minutes to describe, but the complexity that's possible is quite impressive. So this is what I came up with as kind of a hack way of implementing this using a finite state machine. It's really a cellular automata, which is a much more complicated thing because every single cell depends on all the other cells. Every cell has their own set of states. But just zooming in on a single cell, this is the finite state machine for that one cell. So we have 2 states, alive and dead. And neither one is an accept state because these are both perfectly valid states for that cell to be in. And if we're in the alive state and we have 2 or 3 alive neighbors, then we stay in the alive state. But if we have less than 2 alive neighbors, we become dead. And if we have greater than 3 alive neighbors, we become dead. And if we were already dead and we have 3 alive neighbors, then we become alive. Otherwise, we stay dead. So really, really simple. But there is some very cool emergent behavior that you can see, where you can start to create a grid of cell states where some are alive and some are dead, and they seem to mimic some lifelike behaviors like moving, reproducing, and so on. It's actually quite cool. So there's a reference down there from Cornell if you want to read more about Conway's Game of Life. And I'll share with you also a website where you can demonstrate some of these. And if we get a chance during the demo, I'll actually implement Conway's Game of Life so that we can see how it works. The only issue with that is there is a graphic library that we're going to need in order to do this, and that's a little bit of a distractor for this class. But anyway, I'll do the best that I can to make sure that you can try this out. All right, so that's basically that, and this is meant to be kind of an introduction to some more advanced concepts, which you'll obviously elaborate on. In particular, in the future, you're going to be creating, for example, an interactive media. You might create game finite state machines to represent the behavior of the characters in your game, like a guard, for example, might have a finite state machine that represents their state. If you've ever played a game, it's kind of ridiculous. The guard will walk around patrolling, and if they see something, let's say, for example, they see something out of place, like a dead body on the ground, then they'll get alerted and they'll start searching around. So they might be in a different state now, right? They're not just patrolling, they're alerted. So they're specifically looking to see what caused the disturbance. They might actually see you. If they see you, that might be a third state where they're actually targeting you. Okay, and so and there are different transitions that are possible. And most kind of comically, in a lot of video games, what will happen is if they see you, they'll look around for you, so they'll stay in the alerted state for a while. They'll look in the place where you last were, but eventually they'll give up on you and they'll go back to the patrolling state, and they'll say, "Oh, nothing left to do but go back to my patrol. I know, obviously one of my colleagues is dead, but what can I do but continue patrolling, I guess." And so anyway, this is not super realistic, but it is a great way to implement some fun game behavior, and that's really quite cool. You can also use finite state machines in compilers, as I was mentioning. So that's a concept for, I think it's 4th year, and so I'll let you deal with that but at a later time. But I wanted to give you an introduction right now so that it wasn't brand new when you encountered it, so that you could have a little bit of a head start when you get into that kind of content. All right, so that's it for now, and I'll talk to you in the next time when we do some demo code.